last time we looked at infinite limits, limits that turned out to equal infinity or negative infinity. Today, we're going to be revisiting a friend we've encountered before. That's limits at infinity. So we're going to let our x value, our input, go to negative infinity or positive infinity. This is better known as end behavior. All right. So why don't you pause, copy this down, and then press play. All right. So we've encountered this before with polynomials. So let's recall how we did the end behavior of a polynomial. So my polynomial here is negative 3x cubed plus 10x squared plus x minus 17. And for end behavior purposes only, all I need to focus on is the leading term, the negative 3x cubed. So if I want the limit as x approaches negative infinity of the entire polynomial, that's the same as asking for the limit as x approaches negative infinity of the leading term negative 3x cubed, okay? So if I'm plugging in a large negative number for x, like negative 1,000, negative 10,000, and I cube it, I'm still negative, negative cubed is negative, and big cubed is still big. So I'm getting a big negative number times negative 3. Two negatives make a positive, and 3 times big is still big. So I'm getting a big positive, which I'll call positive infinity or infinity. So off to the left, the graph is veering up. Now, same polynomial, x approaches positive infinity. Again, all I have to focus on is the leading term, negative 3x cubed. And now if I'm plugging in a large positive number and I cube it, I'm still a large positive number. Negative 3 times a large positive is now a negative number and big, right? So I'd call that negative infinity. So, I mean, I've determined that if I were to graph the extremes of this polynomial, way off to the left, my y values are getting large. Way off to the right, my y values are getting large negative. So I know the end behavior. Okay. All right, now we're going to take this idea from polynomials and we're going to try and do it for rational functions. So we're going to try and determine the end behavior for rational functions. And there's a very nice trick or technique we're going to use most of the time. So for a rational function, to determine the end behavior via limits, we will divide the numerator and the denominator by the highest power of x in the denominator. Now, it's not clear why this will help us, but hopefully the examples will show it to us. So let me just emphasize, we're going to grab the largest power of x in the denominator and divide the top and the bottom by that largest power of x. Okay, all right, let's check it out. All right. So again, I'd ask you to pause, copy the problem down, and maybe this down, and then I'll work through the problem. All right, so here is a rational function. It's a polynomial divided by a polynomial. And I'm going to try and take the limit as x approaches negative infinity. So limit x approaches negative infinity of my 3x cubed minus my x plus my 7 all over my x cubed plus my x squared. Okay. All right. Now, the last screen said the technique we're going to do is we're going to look at the highest power of x in the denominator. That's an x cubed. And I'm going to divide the top and the bottom by the x cubed. So I'm going to divide by multiplying by 1 over x cubed on the top and on the bottom. So I said divide by x cubed, but that's the same as multiplying by 1 over x cubed, okay? All right, let's see what happens. I'm going to run the 1 over x cubed through both parentheses. So I've got limit as x approaches negative infinity. Now 3x cubed times 1 over x cubed, the x cubes cancel, I'm just left with a 3. Negative x divided by x cubed, well, I'd be left with 1 over x squared. The x would kill off one of the x's in x cubed, leaving 2 of them still in the denominator. Now 7 times 1 over x cubed, nothing much is happening there, so I think I just have 7 over x cubed. That's on top. Now downstairs, x cubed times 1 over x cubed, the x cubes cancel, and we're left with a 1. X squared times 1 over x cubed, the 2 x's from x squared cancel with 2 of the x's from x cubed, leaving 1 x still down below there. So I think I have a plus 1 over x coming out of here. All right. So if we want to zoom in, that negative x times 1 over x cubed, that would give me a negative x over x cubed. And the x cancels with one of those x's, leaving a negative 1 and an x squared down below, okay? That's how I got that -1 over x squared. All right, let me erase that so it gets out of our way. All right, now it's not clear why that is of any benefit to us, but the next step hopefully makes it clear. Let me think about plugging in an enormous number in for my x's now. X squared, if I plug in a big negative number, x squared is a huge positive. 1 divided by a huge positive, that's 0. 7 divided by this enormous negative number cubed, well, that's an enormous negative number in the denominator. 7 over huge negative, that's really, really close to 0 again. 1 divided by a huge negative number, well, 1 over a huge negative is negative, but it's pretty close to 0, and we basically call it 0. So when I take the limit of 1 over x squared, 7 over x cubed, 1 over x, as x gets big and negative, these fractions are all going to 0. So the limit's going to give 3 minus 0 plus 0 over 1 plus 0, all right? Which will just give me, what, 3 over 1, which is a 3. So in slow motion for one of these, let's look at the 7 over x cubed. Limit x approaches -infinity, 7 over x cubed. All right, well, a negative number cubed is going to be a big negative. So I've got 7 over a big negative. Like 7 over 10 trillion, that's like minus 0.0007 or something like that, right? It's tiny, yeah, it's negative, but it's really, really close to 0. So we basically say that is equal to 0. So if I'm plugging an enormous number into the denominator, it's going to be either positive enormous or negative enormous, but either way, 7 over an enormous thing, positive or negative, is basically 0. So that really clears up a lot of parts of our rational function, and I get a limit of 3. Now, from the right, so as x goes to positive infinity, I'm going to do the exact same thing, but I'm going to skip showing you the arithmetic because it's all the same. So when I run the 1 over x cubed through, again, I get the same exact thing here. X approaches infinity, I'm going to get a 3 minus a 1 over x squared plus a 7 over x cubed and a 1 plus a 1 over x. Okay, now if I plug in big positive numbers, I'm still getting enormous denominators and small numbers divided by enormous denominators, like 7 over the infinite is 0. 1 over huge positive, it's 0. 1 over huge positive, it's 0. So this is again 3 minus 0 plus 0 all over 1 plus 0. So that's just 3 as well. So it looks like as x goes way off to negative infinity, my y values get close to 3. As x goes way off to positive infinity, my y values get close to 3. So if you want to see graphically what's going on, let's say here's that height 3. As x goes way off to negative infinity, it looks like my y values are getting close to 3. And as x goes way off to positive infinity, it looks like my y values are getting close to 3. So we call that horizontal line, y equals 3, a horizontal asymptote, because the function way off on the left and the right edges starts to hug that horizontal line. So a horizontal line, y equals c, is a horizontal asymptote of the function if either the limit off to negative infinity is equal to c or the limit off to positive infinity is equal to c, where c is some finite number, including 0. I mean, c could equal 0. Like if these two limits had equaled 0, then y equals 0 is the x-axis, and my graph would hug the x-axis, way off on the left, way off on the right. All right, let's try that a couple more times. Okay, so let's look at the end behavior of this rational function, right? Seems like you're really close to me. Need my space. All right. So I've got a rational function, poly over poly, and I'm going to do the same old trick. I'm going to look for the highest power of x in the denominator. I see an x cubed, and I'm going to divide the top and the bottom by that x cubed. All right, so let's check it out. As x approaches negative infinity, 6x to the 4th minus 7x squared plus 5, 2x cubed plus x plus 1. The biggest power of x was an x cubed, so I'm going to multiply the denominator by 1 over x cubed. And I'm going to multiply the numerator by 1 over x cubed. As long as I do the same thing to the bottom and the top, I've just basically multiplied it by 1, which hasn't changed the function. Okay, so let's see what happens algebraically. All right, 6x to the fourth over x cubed. 3 x's cancel with 3 of the x's there, leaving 1 x behind in the 6x to the fourth and the 6. So I think I get a 6x surviving. That was 6x to the fourth times 1x cubed. Over here, 6x to the fourth, 1x cubed. I get 6x to the fourth over x cubed. And the rules of exponents say I subtract my powers. So I get 6x to the fourth. Or 3 of these x's cancel with 3 of those, leaving 1 of them in the numerator. Okay. All right, I'll probably erase that in a second. Now, x squared over x cubed, both x's cancel with 2 of the 3 x's, leaving 1 x in the denominator. So I think I have a -7 on top and an x downstairs. So a -7 on top and an x downstairs. Plus 5 times 1 over x cubed, so that'd be 5 over x cubed. Right. Now 2x cubed times 1 over x cubed, the x cubes cancel, I'm left with a 2. X over x cubed, x cancels with 1 of the x's from the x cubed, leaving 2 x's in the denominator. So I think I get a 1 and 2 x's in the denominator, so it's positive 1 over x squared. And then 1 times 1 over x cubed is 1 over x cubed. All right. Now, normally I'm afraid of denominators, but when I'm going to the infinite or the negative infinite, if x is in my denominator, I know those little fractions. If it's a finite number over the infinite, that's 0. And it doesn't matter whether it's finite number over negative infinity or finite number over positive infinity. Either way, it's 0. So I think this guy, if I erase a little bit of that, this guy, well, x approaches negative infinity. Let me just take care of the fractions first of all. I'm getting a 6x minus a 0 plus a 0. I'm getting 2 plus a 0 plus a 0. Remember, a large negative number, cube it, that's still a large negative. 5 over a large negative is a tiny fraction that's negative, but pretty close to 0. So we call it 0. Okay. All right, so this simplifies to the limit as x approaches negative infinity of 3x. Which is equal to, well, 3 times large negative infinity, okay? All right. Now, I'm going to have you note that this is interesting, though. Towards the end there, this expression looked like it was linear, okay? And that's going to be important, and I'll touch on that in a minute. Now, as x goes to positive infinity, if I want to just limit as x goes to positive infinity, I'm just going to skip a bunch of steps because they are exactly the same as what I just did. Like divide by 1 over x cubed, plug in the infinite, those fractions will still go to 0. So skipping some steps, I get x approaches positive infinity of 3x. And that's going to go to positive infinity. If x is large positive, 3 times large positive is still a large positive, okay? So everything through here was exactly the same, whether I plugged in negative or positive infinity. Because like 5 over a large positive number cubed is 5 over huge positive. And that's a fraction positive. Sorry, it's a tiny number positive, but really close to 0. So I'll call it 0. And again, I'm seeing linear, okay? So if the limits at infinity yield a linear function at the end, then we have a slant asymptote of slope m. 3 in our example. Okay. All right. So what that means graphically is off to negative infinity, my graph's going to head down to negative infinity, but it's going to look linear while it does it. like linear with a slope of -3. So eventually, as x goes to -infinity, my graph is going to look like it's got a slope of 3 heading down to infinity, -infinity. And off to positive infinity, my y values are going to veer up, but they're going to veer up with a slope of 3 as well. So my end behavior is going to look linear, okay? Which is kind of cool. All right, one last example. How else can it go about? Not easy to. Okay, so last example. Another rational function. If you look back on your notes, you'll see the first example we did, the degree in the numerator was an x cubed and the degree in the denominator was an x cubed. Second one, the degree in the numerator was more than an x cubed. It was next to the fourth, and we got that slant asymptote. And now I've got an x cubed over an x to the first. All right, so let's see how this affects anything. Okay, so let's do the left-hand limit. X approaches -infinity. I've got x cubed plus 7x over x plus 3. And again, I'm going to look for the highest power of x in the denominator. It looks to be x to the first. And I'm going to multiply both sides, top and bottom by 1 over x. Okay, and then I'm going to simplify it. So x cubed times 1 over x, well, 1x cancels from the x cubed, leaving 2 behind. And then 7x over 1 over x, well, the x's cancel, leaving a plus 7. And downstairs, x times 1 over x is just a 1, and 3 times 1 over x is a 3 over x. And again, as hopefully it's becoming familiar, when I have 3 over the infinite, 3 over positive infinity, 3 over negative infinity, doesn't matter. Finite number over the infinite goes to 0. So that thing is just going to 0. So it looks like I'm getting the limit as x approaches -infinity of x squared plus 7 over 1. Okay. All right, so if I plug in a large negative number for x and squared, I'm getting a really big positive number. And then I'm adding 7 to that really big positive number. So it's still a really big positive number. And then I'm dividing by 1. So I think I'm still a big positive number. So that was in slow motion, big positive plus 7 over 1, which is a big positive number, positive infinity. All right, if I approach x, if x goes to positive infinity, again, I'm going to skip some steps here because it's all the same. This step would be the same. And x going to positive infinity, 3 over positive infinity is still going to 0. So I think I'm getting limit as x approaches infinity of x squared plus 7 over 1. And a big positive number squared is still a big positive number. So you know what? It looks like every step was pretty much the same in both cases. It won't always be like that, but the 3 over x step, x approaches positive infinity, x approaches negative infinity, either way, that fraction is going to 0 for both cases. All right, so for this guy, it looks like the end behavior way off to the left and way off to the right are both positive infinity. And you'll also know that it turned out to look like a quadratic. So I'm thinking it has sort of a parabolic shape on both sides, way off to the right and way off to the left. All right, but big take home for rational functions, find the highest power of x in the denominator, and then divide the denominator and the numerator by x to that highest power.